Answering this question is really important because it's within this diversity of cells that are within the cancer lie the roots of drug resistance and metastasis, spread of cells to distant parts of the body that ultimately kills a person. How can we answer this question? How do these cells arise? Well, we get a clue from listening to the pathologists who have told us that cancer is a caricature of normal development. Here you see a picture of a normal mammary gland, and reflected in that picture is the cancer. The cancer is called that because of the Greek, karkinos, which means crab, because the ancient physician, when they found a cancer, would see that all of the blood vessels that fed the cancer looked like the legs of the crab. Crab, karkinos, cancer. I'll get back to the importance of that at the very end. So, the pathologists have told us that cancer is a caricature of normal development. What we've done is to look at the roots of cancer in the roots of development, looking at the development of the mammary gland starting at the very earliest time in the embryo. And we made a startling and unexpected discovery. And that is that the stem cells that generate the mammary gland in the adult, triple-negative breast cancers, seem to morph themselves into this type of very primitive cell. That is the most plastic cell in the mammary gland. It is designed to give rise to different cell types. And so what happens in cancer is they reprise an old program, the one used at the beginning of development, to gain their special powers that have evaded physicians for so long to effectively treat them. So the features that we find in these fetal mammary stem cells are now starting to give us clues as to how to treat metastatic breast cancer. Because just recently we've discovered a previously unsuspected pathway. Again, how these cells reprise a primitive embryonic strategy that's involved in the normal movement of cells from one place to another, enabling the cells that move to start setting up shop in that new site. These are embryonic-like cells in an adult body that provides beautiful opportunities for selective therapeutic intervention. We're extremely excited about this. So let me just sum up by saying the following. In Greek mythology, it was Heracles who crushed Karkinos. Let us think of cancer research as our Heracles, because I strongly believe that it is only cancer research that will turn cancer into the four-letter word that every patient wants to hear. Wrong. Thank you. It is my great pleasure to introduce my colleague and neighbor with whom we're already collaborating, Dr. Suchak.
Thank you very much, and it is an extreme pleasure to be here with you and to share some of our insights into cancer and the cutting edge of what's happening right now in this field. And I'm Susan Keck. I'm the director of the NOMA Center for Immunobiology and Microbial Pathogenesis. And I'm an immunologist, so you might be wondering, what's an immunologist doing up here at a cancer panel? And that's because we now have evidence, undeniable evidence, that our immune system can be unleashed to fight cancer. And a particular cell type in our immune system called a T cell is critical to this process, and that's what I study. I'm trying to understand how T cells form, how they function, and how they help us fight infectious disease, and how they can help us fight cancer. A year ago, when I turned 45, it was a very personal time for me, because that was the age at which my mother died of breast cancer. And as painful as it was for me to watch her die, as I'm sure many of you have also experienced your loved one, it's a tragic, atrocious process. And as a young teenager, it really affected me. But what I saw in my mother when she was dying was extreme strength and courage, and in ways I've never seen before. And that I saw as gifts that she was giving to me for me to pursue my own dreams and my own passions and scientific research, to study and to never give up on these major challenges. Now, I haven't been studying cancer as long as my friend Jeff here, and that's in part because it's only been in the last decade that us immunologists have been empowered now to fight, to use the immune system to fight cancer. And for many years, the cancer researchers have been looking for magic bullets. What are these drugs selectively that we can find that can be used to precisely target the immune system, the cancer cells? Let's see if it's going there again. These magic bullets can precisely target the cancer cell but not hurt the healthy cells. And we know we've fallen short of this goal tremendously with the very blunt weapons that we have of chemotherapy and of radiation. Let me just run through that again. Sorry, I went too fast. Because what we know now is that these magic bullets are actually our T cells. They've been inside our bodies all this time. And now we have the power to use these T cells like magic bullets to go on and to attack and destroy the cancer, because that's what T cells were built to do. T cells are built to go and search out and destroy the unhealthy, the stress, the damage, the infected cells, and that's what they're able to do. But there's a big challenge, and the challenge is that why doesn't this work in our cancers all the time? Because T cells, when they enter the tumor, the environment is so hostile, it's so repressive to the functions, it actually turns the T cells off, and it stops them from attacking the cancer. And this is the basis of immunotherapy, a revolutionary form of medicine that probably many of you have heard about already. Maybe some of you have actually been receiving. What immunotherapy is doing for cancer is using drugs that can stimulate and re-energize our immune system, and particularly our T cells. These are one of the vital targets of immunotherapy, to re-energize them to attack and destroy the cancer and return to a healthy tissue. So imagine if, taking from Jeff, imagine if our immune system could cure cancer like it does a viral infection. And one thing that our lab is trying to understand is what are these breaks that are stopping the T cells from functioning in this tumor microenvironment? And can we use that information to then stop the T cells from listening to those breaks, having them evade those breaks, and be able to regain function? And can we design T cells that are better, more fit, able to last longer and work harder in the tumor to destroy these tumors? So thank you very much for joining us on this pursuit. And now I'd like to introduce Diana Hargrave.
Thank you, Sue. Yes, my name is Diana Hargreaves, and I am an assistant professor in the Laboratory of Molecular and Cell Biology here under Tony Hunter. And I've been here for just about 2.5 years. And like many of you, I have family members that have been affected by cancer. My father is undergoing treatment for prostate cancer right now. And although I'm very aware of the side effects that accompany these therapies, such as chemotherapy and radiation therapy, it's very difficult to watch a loved one go through this, and also to be aware of the sort of permanent and lasting effects that these therapies and treatment can have. And so we're all after that precision medicine, that medicine that can eradicate the cancer but leave the healthy cells intact. And you heard from Sue about this really revolutionary new approach of immunotherapy. We're interested in a complementary approach, which I'll call tweaking the epigenome. So the epigenome refers to this chemical layer of chemicals. This is very important for basis for why, for example, your brain cells are sharing hormones. But it turns out that cancer genes are flagged. In particular, cancer-promoting genes are flagged. In fact, the cancer cells like pancreas are being flagged to really produce very high levels of these tumor-causing genes. And in fact, in many cancers,
In their eyelids. Maybe the cells of the eyelids don't accumulate. Turns out that's not true.